So you know that feeling, right? You opened your fridge, you've just been grocery shopping, it's completely full, and you realize there is absolutely no room for anything new.
And you have to make a call.
Exactly. You instinctively make, well, an engineering decision. You run a quick algorithm in your head to figure out what's the least useful thing in there. What are the stale leftovers hogging all the space?
That decision, that constant process of managing a limited resource is it's fundamental to how high-speed computing works. They have a small, very fast memory called a cache, and when it fills up, something has to go.
Our mission today is a deep dive into the engineering behind that strategic decision-making. We're going to look at cache eviction policies and then see how those ideas scale up inside, these massive distributed systems.
And we're using Erlang's Mnesia database as our prime example.
Yeah. The goal for you, listening, is to get a shortcut to understanding the critical trade-offs engineers are making every single day.
It's a constant struggle. They're trying to minimize latency and maximize what we call the cache hit rate. It all comes down to deciding what gets the boot and why.
Okay, so let's start with the basics. We have this limited cache memory.
Right.
A new item needs to come in. How does the system decide which piece of data is the weakest link?
That is the core algorithmic conflict, and the choice of which policy to use. It depends entirely on the workload you expect. For example, if you're handling lots of temporary sensitive data, you might start with something called time to live.
TTL.
TTL, yeah.
And that one's pretty simple. You just assign a fixed expiration date, basically.
Timestamp. And when the clock hits 0, that data is gone. It doesn't matter how popular it was.
Which is perfect for things like temporary session tokens, right?
Yeah.
Where having stale data is actually more dangerous than losing it.
For sure. But the trade-off is huge. You are completely ignoring usage. You could have a data block that everyone is hammering, but if its time is up, TTL just throws it out. No questions asked.
Okay, so that's a bit blunt. We need something smarter. A system that prioritizes actual demand, not just how old something is.
And that brings us to what is, I think, the industry default for a lot of applications.
Least recently used LRU.
Exactly. LRU is based on this idea called temporal locality.
Meaning if you just use something, you're probably going to use it again soon.
Right. So the system looks for the item that's gone untouched for the longest time and evicts that one.
That sounds incredibly smart.
Yeah.
So if it's so good at predicting future use based on recent history, why isn't it the solution for everything? What's the practical downside?
The downside is the overhead, the bookkeeping. To keep track of the access order, the system has to constantly update a timestamp or shuffle data around every single time an item is accessed. With a massive cache, that gets really expensive.
I see.
And even worse, LRU is really vulnerable to a failure pattern called cache thrashing.
Cache thrashing, what is that?
Okay, so imagine you're looping through a set of data that's just a little bit bigger than your cache. The system brings in item 1, 2, 3, all the way to 10. When it needs item 11, it has to evict something, so it evicts item 1, the least recently used.
But the loop needs item 1 again right away.
Exactly. So it has to load item 1 back in, which forces it to evict item 2. And on. You never get a hit because the moment something is loaded, by the time the loop comes back around, it's the oldest thing in the cache and gets thrown out.
Yeah. So LRU is great, but it works hard. You can trick it. So moving on, there's a policy that tries to solve that by looking at long-term value instead.
Right. That would be least frequently used, or LFU.
LFU.
LFU shifts the metric completely. It doesn't care when you last touched something. It only cares how many times you've used it in total.
So it evicts the least popular item.
The least popular, yeah. This is great for systems where, a tiny subset of your data accounts for almost all of the access.
But LFU has its own famous flaw, right? The cold start issue.
The cold start issue, correct. A brand new piece of data, which might be super important, starts with a usage count of 0.
And before it gets a chance to become popular.
A cache flush happens, LFU sees that 0 count, and boom, it's gone. It's the paradox of the newcomer. Plus, the bookkeeping is potentially even worse than LRU because you need a counter for every single item.
That tension is fascinating.
Yeah.
Recent popularity with LRU versus long-term popularity with LFU.
And to solve the flaws in both, engineers started creating hybrids.
Like segmented LRU.
Exactly. SLRU is designed specifically to protect those popular long-term items. It splits the cache into 2 parts, a sort of probationary area for new items and a protected area for items that have proven their worth.
So a one-hit wonder, that thing that would have tricked LRU, gets kicked out of the probationary section without ever touching the really important stuff.
Precisely. It can't displace a consistently popular item.
And then there's the real curveball, most recently used, MRU,
Yeah.
where you actually evict the data you just accessed. That sounds completely backwards. Why would anyone do that?
It sounds backwards, but it exists because not all data follows that temporal locality pattern. Think about scanning a huge database index or streaming a file.
Okay, a sequence.
A sequence. Once you read item 1, you're probably moving right on to item 2, and you're never going to look at item 1 again. In that case, the most recently used item is exactly the one you're finished with.
So for certain cyclic or sequential patterns, MRU can actually beat LRU.
Surprisingly, yes.
Okay, so we've optimized our local fridge. We get the trade-offs. But what happens when we scale this up to, like, a networked warehouse? A distributed system with thousands of processes all running at once.
That's the pivot point. We're moving from theory to a very concrete, high-demand scenario, something you see a lot in the Erlang ecosystem.
Right.
Imagine you have 10,000 processes that all need to read from a single shared resource. Say, a pool of available network connections.
The traditional Erlang way would be message passing.
It would. Every process sends a request message to a single server process that holds all the data.
But if 10,000 requests hit one server's mailbox at the same time,
You get an instant severe bottleneck. The server just gets flooded and performance grinds to a halt.
so to get around that choke point, Erlang has a special tool.
It does. ETS, or Erlang Term Storage. It's an engine for lightning-fast, constant-time access to huge amounts of data right inside the Erlang virtual machine.
So processes aren't messaging a server anymore.
No, the data is just there in an ETS table, ready for direct concurrent reading.
And optimizing that access is where the engineering gets really interesting. You start looking at configuration flags, like read-concurrency. True.
Yeah, what's so fascinating there is how the designers fine-tuned ETS for multiprocessor systems. Turning on read concurrency makes simultaneous reads incredibly cheap.
But there's a catch.
There's always a catch. The warning is that if your application switches between reading and writing a lot, that optimization, the synchronization overhead, might actually make things slower. It's a calculated risk built for read-heavy bursts.
And that whole philosophy prioritizing speed for specific workloads, that sets the stage for Mnesia.
It does. Mnesia is the distributed database management system built on top of Erlang. It's designed for things like telecommunications, systems that need really high fault tolerance, and what they call soft real-time behavior.
Mnesia basically takes the raw speed of ETS and wraps it in all this distribution logic.
And it has this key feature called location transparency. As a programmer, you don't care what physical server the data is on. Mnesia just figures it out.
Which lets you do incredible things, like move tables from one machine to another while the system is live and even handling writes.
And Mnesia gives the engineer explicit control over durability. You're basically applying our caching choices from earlier, but at the database layer itself.
Using ETS under the hood.
Exactly. So you get three main flavors. The fastest is RAM copies.
All in memory.
All in memory, living in ETS tables. Maximum speed, but if the node crashes, that data is gone. You have to handle saving it to disk yourself.
Okay, then for more safety, you've got disk copies.
With disk copies, the data is in RAM and it's logged to disk, so writes hit both. It's durable, but still fast for reads.
And the slowest, but most memory-efficient option
is disk-only copies. The data lives only on disk, usually in a system called DETS, and it's only pulled into memory when needed.
Now, despite all these speed-focused options, Mnesia's default behavior is all about safety. It defaults to using ACD transactions.
Right. Atomicity, consistency, isolation, and durability. These properties guarantee that complex operations, wrapped in what they call a fun and run-through Mnesia.transaction, are reliable, even when everything is distributed and concurrent.
Isolation is the really critical one there. When you have so much happening at once, it's what prevents that nightmare scenario, the lost update problem.
The lost update problem is terrifying. I mean, imagine two processes trying to give an employee a raise at the same time.
They both read the old salary.
They both read the old, stale value. Without isolation, the first process writes its update, and then the second process just overwrites it. The first raise is just gone.
Vanished.
Mnesia's transaction system prevents that. It uses locking to make sure it's as if each program had sole sequential access to the data.
But that locking and coordinating across a whole network of nodes, that can add latency.
It can. So to deal with that, Mnesia has some advanced tricks like sticky locks.
Sticky locks.
It's a really clever network optimization. If a table is copied across multiple servers and one server is doing a lot of repeated writes, Mnesia uses a sticky lock to keep the lock local to that node.
So it doesn't have to talk to the whole network for every single write.
Exactly. It reduces that expensive network chatter, which boosts local throughput.
This entire conversation, it all leads to this final crucial trade-off. Transactions give you safety, but the overhead can absolutely crush a system that needs insane throughput.
So Mnesia gives you an escape hatch, an explicit intentional one.
Dirty operations.
Dirty operations.
Yeah.
Functions like Mnesia.dirtyRead or dirtywrite that bypass the entire transaction system. You're telling the database, I know the risks, I don't need the safety net for this one.
And the reward for taking that risk.
It's huge. You get significantly higher throughput, potentially 10 times faster than a full transaction.
But the cost is that you give up atomicity and isolation.
You do. You lose the guarantee that the operation either fully succeeds or fully fails, and you lose all that locking protection.
This really forces engineers to become, well, data philosophers. They have to look at their data and classify it by risk.
Is this data that absolutely must have AC safety, or is this data where just having it available and fast is more important than perfect consistency on every single write?
So we've really covered two critical landscapes of optimization today.
Yeah.
First, you're choosing the right cache eviction policy, LRU, LFU, TTL, based on how you think your data will be used.
And second, you're choosing the right data access method, a safe ASCII transaction versus a fast, dirty operation based on that safety versus throughput trade-off.
And that leads to a final thought for you to take away. We've seen that to get the absolute maximum speed, sometimes you have to deliberately give up safety. You use these dirty shortcuts. So if you were designing a complex mission-critical system, maybe for routing emergency calls or tracking high-frequency trading, knowing that dirty operations are 10 times faster, which core pieces of data would you mark as safe, requiring transactions, and which would you allow to be dirty for that massive speed boost? How do you even begin to quantify the risk of a lost update against a 10 times performance gain?